All right, welcome back again. So, now we will start studying more systematically. I think we have given essentially 3 lectures, 3 half an hour lectures on the motivations. So, but it is important to understand, even though it was motivation, there are points for you to go through it and solve the exercises, and all that we will be recalling one by one as and when it is required. So, we will give a formal definition of a distribution now. Okay. Distribution. Okay. In simple terms, a distribution is an element of T prime of n. A distribution T is an element of the dual d prime of omega, because d omega is given as a topological vector space, locally convex topological vector space, and d omega, the only trouble is it's not metrizable. Other than that, d omega has all the properties which we have discussed in detail. Okay. So, that is T is a mapping from d omega to R such that one T is linear in the sense of linear algebra. Okay. That is T of alpha phi 1 plus beta b 2 is equal to alpha T phi 1 plus beta T phi 2, okay, for all phi 1 phi 2. So, I am giving in detail, though you know already, in d omega, and for all alpha beta belongs to R. Okay. So, it is linear. And the second one, let me write it here itself then. Second one, T is continuous. This is you have to understand. We will later give you an equivalent definition in terms of the estimates, which is you have to understand the topology. So, I may not prove it, but we will give you the thing. T is continuous, that is phi k, this is not a compact set, a sequence, phi k converges to 0 in d omega. You have to understand. So, whenever now you have lot of different convergences. So, it is important to understand various convergences. So, you have to specify your convergence takes place in which space, and you are going to see more and more spaces later, such that is if phi k converges to 0 in d omega, then d phi k, and d phi k is a real number, goes to 0. This is in R, you do not have to specify it. So, these are the two conditions of the distribution. So, therefore, d prime of omega is the set of all distribution, is the set of all distributions. Now, I am going to give you a lot of examples. So, okay. So, that is what the definition. D prime of omega is the set of all distributions. Okay. So, let us start with one example. So, maybe I will use a different color example. So, you will have lot of examples. So, you will see also new state. So, let us start with an example. Suppose f is locally integrable. The notation of locally, now I will not say keep on telling, is an f is a locally integrable, wherever it is an omega or r or whatever, any locally integrable function. So, define T f. So, for first example I am writing everything, later I may not write each and everything, is up to you too, but when you are studying this distribution theory for the first time, make sure that each time you write all the steps in the beginning, okay, by Tf of phi is equal to integral of. So, what are the steps you have to do it? Integral of f phi, this is true for all phi, of course for all phi in d omega. So, you have to do 3 steps. One, the well definedness of the definition, whether Tf is a finite quantity, because Tf is defining, that is what you have to do it. Second thing, you have to check the linearity, and third one is the continuity. Okay. Many cases it will be easy and certain cases it may not be. So, make sure that. So, the one Tf modulus of Tf of phi, you see. So, that is the first thing I am checking, is same as modulus of integral of f phi. Why this is finite? This is finite because this integration is basically on a compact set, because phi is in d omega. So, there is a compact set. So, this is equal to is nothing but modulus of f phi, and then the integration is taking only on a compact set, you see, and support of phi is contained in some compact set, or it is or equal to compact set. And f is locally integrable means the integral of mod f is finite. So, that gives you finiteness. So, why I am writing, even though it is trivial, these are the steps you have to define, check it for even for non-trivial examples. Okay, so, that is a finite quantity. So, the implies Tf is well defined, is well defined. Okay. The linearity is trivial, that is the linearity of an integration. Linearity is trivial because it is an integration, you know that integration, integral of f1 plus f2 is equal to integral of f1 plus integral of f2. So, is trivial, follows from the linearity of the integration. What about continuity? This you have to check it. It may not be trivial all the time. Continuity. So, let phi k, this k is different from this k. Okay. So, do not get confused. Phi k goes to 0 in d omega. What does that mean? Phi k and all its derivative, all multidimensional derivative goes to 0 uniformly in k, and support of phi k contained in a compact set k. So, I may maybe it is not nice to use this k here. So, probably it is better to use phi m. Okay, phi m goes to 0. Okay. So, this implies there exists k. Okay, support of phi m contained in k. You have to write down such tips, and d power alpha of phi m goes to 0 uniformly. Uniformly. Okay. So, but for this particular problem, it is enough to, you do not need all the derivative convergence. It is enough to have phi m goes to 0 uniformly. So, now we want to show this one, integral of f phi m over omega. This is same as integral over k, because there is a fixed compact set f phi m, you see. So, how do you, with this there is a something you can immediately understand, phi m goes to 0 uniformly, and in particular point wise. So, in particular f phi m goes to 0 point wise. Okay. And you can also see that integral of f phi m modulus of f phi m is less than or equal to mod f, and this is integrable on k, integrable on k. How do you do? So, you have a sequence which goes to pointwise, and this comes from here. It's a it comes also it comes also is a single compact set. So, FEM can be estimated with some constant. Of course, there will be some constant. Otherwise, Pm goes to 0. You can uniformly you can find epsilon, and for large m you can say that one, but doesn't matter. This is fine. So, you have a estimate by an integrable function, and then you can apply some of the convergence theorem like Lebesgue dominator convergence theorem. So, this immediately implies you this goes to 0 by Lebesgue dominator convergence theorem. You may be able to do it in. So, you have Pm converges to 0 implies integral of Pm converges to 0. This is nothing but Tf of Pm. So, it is a very easy thing, it is not. So, why I wrote it separately, these are the 3 steps you all the time you have to do. Many times it will be easy, or some of the things will be easy, but not all the time. Okay. Okay. So, let us go to another remark, another example, very interesting example. You will see the importance little later. Very nice one. Consider this function f of x equal to 1 over x. This is defined, right? Is defined for all x not equal to 0. Is log not equal to 0. X is in R. But this is not locally integrable. That is a problem. So, you cannot define as a distribution directly. So, that implies directly it does not define a distribution. By our knowledge, it does not define a distribution. But then there is an associated, you will see that why then there is a there is a principal value integral. So, there is a what is called a Cauchy principal value, Cauchy principal value principal value. Okay. So, which we denote by a PV of 1 over x. So, I am defining a mapping from PV of 1 over x of phi is equal to limit epsilon tends to 0 of integral over 1 over mod x phi of x dx with mod x greater than or equal to epsilon. So, in this case all the questions above are not trivial. Okay. So, PV I just defined a mapping, show that it is well defined. The first thing is these are all exercises which I will leave. That means you have to show that this limit exists, epsilon tends to 0. It is not immediately trivial to, you cannot take epsilon tends to 0 and put it minus infinity to t infinity, because 1 by mod x is then is not locally integrable. So, you cannot put a characteristic function and take limit inside. Of course, I can write this as integral of characteristic function of mod x greater than or equal to thing 1 by mod x x. But then you have the pointwise convergence, but you cannot take limit inside the integral. So, you have to play a little trick to show that it is well defined. Linearity is fine, easy, and then show continuity. Okay. So, this is a kind of a little bit of, you will see why what this exactly, little more you can see that. Okay. But then there is an immediate remark. Okay. This is 1 by mod x f x equal to 1 by mod x x not equal to 0, x is in Rn is locally integrable for n greater than or equal to 2, locally integrable for n greater than or equal to 2. Only for n equal to 1 this is not locally integrable, but 1 by mod x is locally integrable for n greater than or equal to 2, and thus therefore it gives you a implies Tf belongs to D prime. Then because we have defined earlier the example, any locally integrable function you can do this one, and we can continue this more on. Okay. You can take example further, not only that one example, you can actually take f to be in LP, which you have already seen the definition for 1 less than or equal to p less than or equal to infinity, and define Tf. So, I do not keep on defining everything, I will just write the definition. So, Tf of phi is equal to integral of Fp. Why this is finite? You have to show the well definedness that you have seen it, because if phi is in d omega, then phi is in LQ, you see, that implies phi is in LQ for all q, for all q, right. So, you apply the Helder inequality to show that it is finite. So, integral of Fe is finite, implies more. So, it is well defined, Fe is finite, and a similar arguments which I have given, you can actually show that. That is what I say, you should work out everything. Tf of Pn, Fm converges to 0. So, to work out, it is exactly what I have done for locally integrable function. For other cases you work out. Tf of Pm converges to 0 if Pm converges to 0 in d omega. So, you see. So, you have a large function. So, therefore, all this LP of omega can be viewed as a distribution. So, this inclusion, I will write more about this inclusion a little later, and probably I will do this at this stage or later. Maybe I will. So, you can view this one. I will have to understand little different way. When I am writing this, this means that if f is in LP, you are identifying, then Tf is in T prime. That is the meaning of that. Okay. That is the meaning. And later we will see, soon we will see, this inclusion is a continuous inclusion. I will tell you, for that I have to define the topology on D prime of omega. So, after that, so I am going to define a topology here soon, or maybe I can define a weak star topology right now. So, weak star topology right now we can define. Why delay it? Topology on D prime. So, this will give you, it is a topological vector space. D prime D prime of omega is a topological vector space. So, of course, if T1, T2 in D prime, then T1 plus T2, these are trivial things to make it a vector space structure. That is the thing, when you have a set, The important thing is to give a vector space structure and topological spaces, making it an algebraic structure and as well as the topological structure, and then link it through its continuity. These operations are continuous. So, it is important to make your spaces what kind of convergence, what kind of algebraic structure, what kind of geometric structure, and how you combine that one should go together. That will make you the topological vector spaces. So, T1 plus T2 phi is equal to T1 phi plus T2 phi and T1 of alpha phi is equal to alpha T1 of phi. No phi 1 there, phi alpha phi if is equal to T1 of phi, and this is true for all alpha also, right, alpha real. So, this is the linear structure, and the weak star topology, is if we say, so you need a definition probably. The weak star topology, the definition is, we say T, a sequence Tm in D prime converges to T in D prime if Tm of phi converges to T phi for all phi in D omega. So, it is a weak star topology, the topology coming from your pre-dual space. That is how you define on a dual space. It will have its own norm topology or strong topology. It may come a topology immediately. In fact, there is also a strong topology on D prime, which I may make a remark later. I will not give you a detail, but if you know certain type of function analysis, you will be able to do that one. So, there is a strong topology which I will tell you later, but then the weak star topology is coming from your pre-dual, and weak topology comes from the dual, because since right now we do not have a strong topology and we are not defined what is D double prime, you can't define a weak topology there, but you can define a weak star topology. So, we will associate with this weak star topologies here. With that weak star topology, okay, all right. With that weak star topology, now look at this f in LP. F in LP of omega, you are associating with a TF in D prime. In other words, this is a kind of an identity mapping, because we are identifying F and TF, and eventually we will not distinguish F and TF, identify F and TF. We will not distinguish, so we will use it, we will not distinguish eventually. Okay. Right now I am distinguishing because you feel you are studying it for the first time. So, when I say that F, you also view it as a map TF. Okay. We will not. That way, this is a kind of an identity mapping from LP to D prime of omega. Okay. Okay, where F going to I of P, I of F, which is actually F, which is identified with the TF, what? Okay. So that. And this is continuous. You can easily see that, you can work out that. That is, Fn converges to F. If you are not convinced, do it as an exercise. If Fn converges to F in LP, then that implies the corresponding TFN family of distributions converges to T in D prime. Okay. So, let me make a. So, in this case we say that Tm, we say that Tm converges to, so the notation is that we say Tm converges to T in D prime. In D prime means in distribution equivalently, in distribution. So, you have to write down. So, whenever this convergence happen in D prime, we say that that convergence is in distribution, which we are going to see in the whole course, and even in the next course we will see this aspect. So, you see, and this notation is already in. So, if such an identity mapping is continuous, we say LP omega continuously embedded, recall your basics, embedded in D prime, and we use the notation. So, when you have a notation as this notation, okay, D prime, you have already there in the preliminaries. So, those who have not gone through preliminaries, this is such a continuous embedding. So, whenever I use such a notation, that means the corresponding identification is and then the map identity map under that identification is a continuous map. So, you have both topologies there. So, you can do that. Okay. And so, yeah, so it is okay. One more thing, yeah, all that even this needs this exercise how to understand properly. You have to, so try to do this exercise. Okay. Again you may need that if something converges in LQ and all that. Okay. For example, if you have a convergence in d omega, you can get the convergence in LQ, okay, which we probably discussed. It is discussed in our elementary. So, let us go to now another interesting example, which some new example. Okay. So, what is it? My example of a Dirac delta. So, with this example I will be able to stop. Example Dirac delta. Okay. So, what you do is that, so let x naught be a, so formally I am defining now. Let x naught be a point in Rn, so very generally, and I define delta of x naught acting at a phi is equal to phi at x naught. Yes. This is true for all phi in D of Rn. So, nothing this is almost trivial to check this. It is very trivial to check the linearity and well definedness and continuity, nothing to really check it. For example, is well defined because it is a point and phi is a continuous function, of course it is C infinity function. Linearity is obvious, continuity is also obvious. If phi n converges to phi in D of Rn, every point it converges, phi n of x naught converges to phi x naught. If you are not convinced, please check it. Okay. So, that check your delta of x naught is in D prime, you see. So, your delta of x naught, you are able to view it as a distribution. But then I want to make some remark here. So, that part is trivial for all of you to do it, but then to understand delta of x naught, you need not have to go to distribution such a strong theory. Okay. Delta of x naught can be viewed as a measure. So, this is the remark I will do. Then you may wonder why we study distribution. We will make that remark. So, delta of x naught can also be viewed as a measure, nice measure actually. How do you define? So, delta of x naught, you need a sigma algebra, my sigma algebra is the power set. So, that is no problem. So, you can define delta of x naught acting at E is equal to 1 if x naught. So, you see what we have defined earlier as an example, you are viewing delta x naught as a mapping from D of R into R, but delta x naught I can define if x naught is in E and 0 if x naught not in E. So, delta x naught is a mapping from the power set of R n to R, and you can verify it is indeed a measure, or you would have studied in measure theory is subadditive and all that. And once you have a measure, so once you have a delta x naught is a measure, the measure develops an integration theory that gives you functions can be integrated, functions can be integrated any measure with respect to that measure. So, the advantage of measure is the normal integration Lebesgue theory is that you have a Lebesgue measure, but for any other measure also you can develop an integration theory. So, integrated with respect to delta x naught. Okay. So, I want to know what is this? So, your integration. So, basically you are trying to integrate, that is what Dirac envisaged, and that was Dirac wanted it. Dirac wanted how delta x naught acts as operators or acts on the functions. So, with the functions f of x, and you can integrate this function with respect to x naught. Okay. So, you can do that symbolically, you may write something like that. So, if you integrate with that with respect to that in R n, you precisely get f of x naught, maybe some assumed continuity or whatever it is. So, you see, and this is exactly what Dirac wanted, Dirac desired. So, what Dirac wanted is more or less done with viewing it as a Dirac desired. But then if you go back to your motivation, you also seen that we want to differentiate the delta x naught. So, he want to get not only the value of f at x naught, he also wanted the value of the derivative of f x naught. For that you need to differentiate delta of x naught, and then that will not remain in the purview of measure theory. So, within that measure delta x naught is understood, but recovering the derivatives there requires some sort of a differentiation, and that cannot be recovered under the ambit of measure theory and creating new objects, and which we will discuss in the next class. Thank you. I will stop it.